To build a perfect circle, you take a fixed center point and trace out every possible location sitting at the exact same distance from it. If you bring a straight line toward that circle, the line can graze the outer edge. A tangent line touches the boundary at exactly one solitary point. This diagram maps a radius drawn from the center outward to that single point of tangency. When those two lines meet, they form a perfect 90-degree right angle. Visually, it looks right, but seeing two lines meet isn't the same as proving they meet at an exact mathematical right angle. Why must it be exactly 90 degrees and not 89.9? Geometry demands proof. And proving a single geometric truth often means looking at the exact same shape through completely different frameworks of logic. We can start with the approach of ancient Greek mathematicians. They analyzed space through strict static logic, working out proofs without numbers or moving parts. They relied on a simple spatial reality. The shortest possible path from any point to a straight line is a perpendicular drop. This maps that rule onto our circle. The point where the radius touches the tangent is the closest that line gets to the center. Every other location along the tangent line sits outside the boundary, making those segments longer than the radius. To prove the tangent must be perpendicular, we assume the opposite. If the line is slightly tilted, the true perpendicular drop from the center is shorter than the radius, dragging the intersection inside. It hits the boundary twice, but a tangent only touches once. Since our line cannot cross the boundary twice, it cannot tilt. The geometry of the circle locks the point of tangency into the shortest path, forcing the intersection to exactly 90 degrees. That static logic holds up perfectly, but modern mathematics gives us a different tool. We can view the circle as a system in constant motion. This graphic shows a secant line cutting directly through the circle, creating two distinct intersections. If you slide the upper intersection down the curve, the 2 points merge, and the secant line locks into place as a tangent. We track the math of that movement using Thales' theorem. We've drawn a triangle connecting the circle's diameter to the circumference. Thales proved that any triangle drawn inside a semicircle will always have a perfect 90-degree angle. As we slide the top point down the curve to merge with the bottom, the secant line morphs into the tangent. The right angle doesn't disappear. It gets pressed directly into the space between the diameter and the tangent line. By watching the geometry shift in real time, the angle's true nature emerges. The limit of that continuous motion dictates a perfect perpendicular intersection. We can remove the physical shapes entirely and look at the exact same relationship through the lens of pure numbers. This plot anchors the circle to an XY grid. We assign coordinates. The radius stretching out is defined by the blue vector AB. The tangent running along the edge is defined by the red vector -b, A. To find the relationship between two mathematical directions, you multiply their intersecting terms to find their dot product. Multiplying A by -b and adding B times A leaves you with exactly 0. In linear algebra, a dot product of 0 is the absolute test for perpendicularity. The coordinates themselves confirm the 90-degree angle through indisputable arithmetic. We started with an intuitive picture of a line touching a circle. We proved it with classical spatial logic, mapped it through moving geometric limits, and calculated it with algebraic coordinates. All three distinct methods arrive at the exact same truth. Understanding how lines interact with curves expands far beyond circles. Knowing how to calculate a tangent is what allows engineers to map out physical motion, track the behavior of light, and build the foundation of modern calculus. Geometry offers multiple paths to the truth. When you look closely at a single mathematical reality through different frameworks of logic, the entire system begins to make perfect sense.